Hey everybody, welcome back. This is Module 12, the Cerebral Cortex, Unit 2. Okay, in this module we're going to take a look at the four lobes of the brain, including what I like to call the wrapping paper of the brain, which is the cerebral cortex. We're also going to look at the various different lobes of the brain, and also all of the cortexes and association areas, or the areas that we think we store most of our memories. We're also going to look at the notion of whether or not we use only 10% of our brain. We're also going to talk about how the brain has this amazing ability to adapt to new experiences and also to deal with damage and trauma. Okay, let's go ahead and get started. All right, so the cerebral cortex, again, like I said, folks, it's the wrapping paper that goes around the brain. In the next slide, I'm going to show you a quick picture. But basically, it's the wrapping paper that goes around every single little crack and crevice, every square inch of the cerebral or the cerebellum, which is the upper part of your brain. And basically what it does is it serves as a gigantic communication network. It speeds up processing, it speeds up communication, and it links all of the different cortexes together. Okay, so when we look at the cerebral cortex is the paper. All of the smaller cortexes are just subdivisions of that wrapping paper. All right, we'll take a look at that in just a second. So the regions of the brain, the four main regions, there are some smaller regions, but the four main regions are called lobes, and we'll take a look at those lobes as well. All right, so if you'll notice here, folks, this region right here, all of this outer covering, all these little cracks and crevices that go in there, the cortex goes inside, even all the way down into this little crack. All right, and you can see that darker orangey color is the cerebral cortex. Okay, so two main divisions of the brain. We have the left hemisphere, we have the right hemisphere. If you are wanting to know what side is left and what side is right, well, it's your left side and your right side. Okay, so your left hand corresponds with the left hemisphere of your brain, your right hand, the right hemisphere. Okay, the lobe and the lobe division, we have the frontal lobe, we have the parietal lobe, and then we have the occipital lobe. In the middle, surrounding the thalamus, is what we call the temporal lobe. Okay, and we're going to take a deeper look at all of those here in just a second. So, frontal lobes. The frontal lobes, and there are several different subdivisions. The frontal lobes are going to basically control speaking, motor movements, judgment, and decision making. This is going to be our, it's kind of a hodgepodge of different acts that we all have to carry out on a daily basis. Usually every few minutes we're carrying out decision making, judgment, or movements. The parietal lobe is going to be responsible for receiving and processing sensory input. Okay, the parietal lobe will be subdivided, and you can see the line right here. The parietal lobe will be subdivided into the visual cortex and we call it the somatosensory cortex, which is motor movement as well as all of your sensory input, with the exception of smell. Okay, temporal lobes. The temporal lobe. This is like the whipped cream that goes around that ice cream cone that I was talking about of the brainstem. All right, it wraps or encases the thalamus. And the temporal lobe basically is going to help handle auditory information. This will be subdivided into what we call the auditory cortex, and we'll talk about that here in just a second. And basically the way it works is each lobe basically will correspond with the opposite ear. So the left side of your temporal lobe will process information from your right ear and vice versa. The same thing is going to happen with the occipital lobe. The occipital lobe is located here in the back of your brain. And this lobe is primarily responsible for vision and how we interpret and process our visual field. And we'll talk more about that visual field here in just a few seconds. Okay, so let's look at the motor and the somatosensory cortex, sometimes called the sensory cortex. All right, so if you look here, so basically the right side of the motor cortex will feed the left body's movements. okay, and then the right side of the motor cortex, this side over here will feed the left. The left hemisphere of the motor cortex will feed the right side of the body. So when you go to give somebody a thumbs up, it's actually coming from the left hemisphere of your brain. The somatosensory or sensory cortex, this is going to be receiving senses as well as perceiving bodily movement. So as your body is being pushed by the motor cortex, the somatosensory cortex will be perceiving how it feels in your muscles and your bones and your nerves and your joints when you take steps or when you run or when you give somebody a high five. Okay, let's look at your auditory and your visual cortexes. All right, so your auditory cortex, again, is located right there, right behind the ears. And your visual cortex is located here in your occipital lobe. All right, it's basically the wrapper that goes, the part of your cerebral cortex that goes around your occipital lobe, okay? Your visual cortex, like I said, is right there. It's going to receive cross information through what we call the optic chasm. We'll talk about that in just a second. All right. But before we get to that, we're going to talk about one of the big myths in psychology and science in general. How much do humans use their brain? So here is the kind of not answer to that question. Do we really use 10% of our brain? And what we do is we see that association areas do not cause any kind of observable response. And association areas are the areas in our brain that are not specifically designated to other functions. So, for example, if you look down here in the bottom right, this is a human's brain. You can see the association areas are these areas of kind of the no color, kind of the outlined areas only, but they're massive. And if you compare them to a chimpanzee, and then you compare that to the association areas of a cat and that of a rat, you can see the association areas or the memory areas or the processing areas. Humans have a much larger size. Okay, so so this is a false claim. 10% of the brain is false. We oftentimes think of the 10% of the brain being the active areas, but what we don't really take into account are these areas of what we call association. And these association areas, they actually, even though they don't respond to electrical stimuli, they are important for processing and storing or interpreting or integrating this sensory information. Okay. So, number 3, is there really a 90% chance that a bullet to your brain would land in an unused area? Is that a question? Well, if it is, the answer is no. So basically, there's lots of studies that have been done. One of the problems is this: our brains are not really unused. The association areas, although they appear to be inactive when they are electrically charged, we are fairly certain that we use a good portion of them. And if a bullet was to strike the brain, there is actually a very high likelihood that your brain will be damaged. And depending on how intense the wound is, it can be quite extensive. Okay. It doesn't even take a bullet. It could be a trip and a fall and a smack on the concrete or falling off of a bicycle. All right, you should always wear your helmets. Okay, so what are the association areas of the brain? This is basically the cortex, which integrates information into learning, remembering, thinking, and higher level functions. All right. Basically, anytime attention is shifted, or like if we're focusing on one thing, then we can go to another, our brain automatically plans, interprets, and then creates counter actions for all of that. We don't even feel it most of the time. Basically, the association areas are also not specifically devoted to a particular motor or sensory cortex. They're not part of the occipital lobe. They're not part of the visual cortex or the auditory cortex. They're not necessarily part of your frontal cortex or prefrontal cortex, as it's sometimes referred to. Speaking of prefrontal cortex, cue next slide. Okay, prefrontal cortex. We do know much about the side effects of damage to the prefrontal cortex, and the reason we know this is because of a guy by the name of Phineas Gage. He kind of begins this whole understanding of the frontal lobes, and we'll take a look at his case here in just a second. But the prefrontal cortex is the very forwardmost part of your brain. It's directly behind and above your eyeballs. So if you were to kind of go in your eyeball, in fact, this is where the practice of lobotomy actually started to take place. And basically, we're certain that these frontal lobes help with judgment, planning, and the processing of new memories. But we do know people that have damage to their frontal lobes may have amazing intelligence scores, but yet they're not going to plan ahead for anything. They may also experience emotional outbursts, as we're going to see in the next case. All right, so moving on. The case of Phineas Gage. Phineas Gage in the 1400s, in the 1800s, pre-Civil War 1800s, he was actually working on the railroad. And he was using what's called a tampering iron. And the tampering iron is this big, long steel rod. And the tampering iron was used to hammer or pound holes into the ground where charges would be placed to help blow up rock or blow up ground to be able to lay a railroad and to lay the railroad quickly. So what happened was this. Phineas goes to put this tampering iron into the ground and hammers. And then all of a sudden, what happens is somehow maybe he was pushing a charge into a hole to be detonated later, or if he went to hit in a hole that already had a charge in it, whatever the case was, you can see this picture on the right, that tampering iron was launched out of the hole and directly into his head. And basically how it went was it entered right here just above his mouth and came out. You can barely see that scar on his head right there. Okay, that scar right there. And it basically damaged greatly his prefrontal cortex. But the crazy thing about his case is he actually was conscious for most of the first few hours that he had experienced the accident. He was traumatized, but he was conscious and was bleeding, but not to the point where he was, not to the point where he died, obviously. And the problem we run into is this, is that people that knew Phineas, they knew him as a kind and conscientious, kind of quiet person, always respectful. But after he had this accident with the tampering iron, he ended up falling into fits of rage and had problems controlling his emotions. He would get very angry at the drop of a hat. He would forget people. He would forget things that he had done earlier in the day, and this was very unlike him. So through the case study of Phineas Gage, we realized is that his frontal lobes could not interpret the emotion any longer because they had been damaged. And that caused emotional reactions in the rest of his behaviors. So what happens is that he basically has a communication issue because of this accident, and his body isn't able to handle it, and he lashes out. He ends up dying about 18 to 20 years later. There was secondary infection that had, he had to go see a doctor, and one of the stories associated with this case study was that he went to the doctor and started coughing, and all of a sudden part of his brain fell out onto the table. Now, I don't know if that's accurate or not. It's probably a tall tale. But anyway, Phineas Gage, prefrontal lobes damage causes emotional reactions in the limbic system. Okay? All right, Broca's and Wernicke's area. Folks, this is almost always on the test, AP exam. So please make sure you have these down. All right? So Broca's area is a part of the brain that is centered in the left frontal lobe, all right? And this is basically involved in expressive language, meaning it is the expression of language. Broca's area is absolutely vital to us being able to create words, to be able to create body language that expresses what we're thinking. We have to have that part of our brain in order to express language, meaning to create language or to speak language. Wernicke's area on the other side, and it's in the center, it's the language center located in the left temporal lobe. They're both in the same general area, but it is involved in receptive language. So here's the crazy thing. Let's just say hypothetically that I had damage to Wernicke's area, but not Broca's. All right, Wernicke's area, if it was damaged, basically what this means is you could come up and talk to me and say, "Oh, how are you, Mr. McCauley? I hope you're having a wonderful day." I would have no idea what you were saying because I could not receive or understand that language. But I could turn around and say, "I don't know what you're saying to me. Get out of my face." I could do that because I still have the ability with Broca's area to express language. And the inverse is also true. If I had damage to Broca's area, you could come up to me and say, "This is a wonderful day. Isn't it nice?" And I could hear all of that and understand and process all of that. But when I went to speak back to you, I would not have the ability to create expressive language. Okay, let's talk about plasticity. Plasticity is the brain's ability to change and adapt. We see an incredibly high rate of plasticity in childhood. As we get older and we reach our full maturity, that rate of plasticity does change, and it usually decreases. So the example that I like to give when I'm talking about plasticity is the idea that most of you have an art form. And if you think of, say, a musician, all right, the more a musician practices, the better the musician gets in theory. All right. And part of that is due to the fact of our brain's plasticity. And that plasticity allows neural networks to become stronger and stronger and branch out. So when you are playing the cello or whatever it might be that you're playing, your brain is actually creating new neural networks that connect how it feels in your hands and the sound in your ears to create beautiful music. And it gets stronger and stronger and better and stronger. And the more you practice, the more you improve your neural communication. That is plasticity. Okay, we're going to skip over that. All right, so how does plasticity work? Basically, what we see is plasticity is the body's ability to rewire or crosswire itself. This is an image of a young girl who has actually had a lot of her brain removed, much of the right hemisphere. You can see that big void right there. She had chronic seizures that actually were causing her to almost die. So neurosurgeons went in and removed a large chunk of her brain. The problem is that initially, when this part is removed, a lot of the function dies. A lot of the function is gone. The person's going to need to relearn how to do all of these things that were in this area that was removed. But here's the crazy thing. All right, due to crosswiring, she can actually move her left side of her body, even though her left hemisphere, which is not supposed to happen, her left hemisphere was able to do the work, at least to some degree. It was able to do the work of both the left and of the right. The right hemisphere controls the left side of the body. All right, she should not have been able to move it. It was gone. All right, the right hemisphere was gone, so her left side should have been just dead, all right, for the most part. But because her left hemisphere realized that the right hemisphere had been compromised, it was able to rewire itself and reroute some of that neural load and actually allow her to continue to use some of her right side. Some of her left side. Okay, so very amazing ability to create new neural networks. All right, neurogenesis is related to plasticity. Plasticity is the brain's ability to rebound from an injury. Neurogenesis is basically creating new neurons and establishing new neural networks. Okay, that is neurogenesis. And it's amazing that our brains can do this, and we do find evidence of this as we go throughout life. Even in our elderly years, our body is still trying to produce new neurons and new neural networks. The only problem is that oftentimes our ability to rebuild or perform neurogenesis has been compromised, or it's not as good as what it was when we were younger. So, okay, so next module is 13. We'll talk about brain organization as well as hemisphere organization and what it means to be conscious. All right, stay tuned. I'll see you soon.